Hello, guys. I am in Connor 111 right now. So it almost feels like we're having class. There's just nobody in here with me. All right, so today we are going to talk about a conceptual introduction to inferential statistics and hypothesis tests. All right, hypothetically, this is, not hypothetically, for real, this is content that you learned about in your business statistics class, but I don't know how much of it you remember. All right, so we're going to pretend like you don't remember any of it, all right? And we are going to go through the conceptuals of why we need inferential statistics. What do the null and the alternative hypothesis mean? What does the result mean? All right, I came to Connor 111 so that you can see this white jiggling over here. This is the document camera on the podium. It's going to step in for the board for me because we would generally do a lot of this class on the chalkboard, which is not an option for us. All right, so we're going to go back and forth between slides in this sheet of paper. And of course, you guys are able to pause, turn off, come back, etc. But so hopefully this will be helpful for you guys in helping to figure out what are we doing these tests, why are we doing these tests, and how do I interpret the results of them. All right, so let's imagine that, I guess I need to do this. Let's imagine that customer satisfaction last year was 92%. All right, so last year we sent a survey to, let's say, 1,000 of our customers. They were randomly selected and they were asked, are you satisfied with the performance from our company, yes or no? And 92% of them said yes. And so this year we do the same procedure. We send 1,000 surveys out to a different random sample of 1,000 people. And this year, customer satisfaction, that those 1,000 people, 93.5% of them said, yes, I'm satisfied. All right, so last year, 92% of the sample said they were satisfied. This year, 93.5% of the sample said they were satisfied. The question is, has customer satisfaction increased? All right, so not just customer satisfaction within the 2,000 people sampled, but overall, all right, across all of our customers, has customer satisfaction increased? Does this evidence tell you that customer satisfaction has increased? I miss all your beautiful faces in class. If you were in here, some of you guys would say, yeah, it's increased. 93.5 is a bigger number than 92. All right, so customer satisfaction has increased. But some of you guys would be a little more hesitant, right? You would be giving me looks like, I don't know, 93.5 isn't that different of a number from 92. Well, what if a bonus gets tied to this? All right, what if the manager has in his or her contract that if customer satisfaction increases year over year, that manager gets a bonus? All right, so now there's money tied to this decision. Are we still as confident in saying, you know, if you were confident before, are you still confident now to say that customer satisfaction increased? We're going to get to figuring out, did customer satisfaction increase? But first, I just want to introduce you to the kinds of real world practical questions that we use this kind of testing for, because it does matter, right? It does matter in business decisions. How about we send out a survey, and on that survey, we ask, we introduce a new product and we ask people how likely they are to purchase that product on a 1 to 9 scale, where 9 means more likely to purchase and 1 means less likely to purchase. And we also ask people about their gender. And when we look at the data from our sample, we see that the women in our sample report a mean of 6.4 on that 1 to 9 purchase likelihood scale. And the men report a mean of 7.0, right, on that purchase likelihood scale. And so we want to know, from a marketing perspective, are men more likely to purchase our product? All right, so we're asking them, how likely are you to purchase it? The men in our sample have a larger mean than the women in our sample, right? And so do we think that this implies that in our population of potential customers, that men on average are more likely to buy this product than women? All right, the evidence suggests it's possible, all right, but if we put a dollar thing here, so we want to be even more confident before we spend money, should we be targeting men in our advertising? Is this evidence strong enough to suggest to us that at the population level, men probably really do prefer our product, and as a result, we should focus on men in promoting and advertising our product? These are the kinds of marketing research questions that get dealt with, all right, on surveys, and that get dealt with in field studies. Our survey in class about ADHD, the marketing implications of the results are going to be a little bit less clear, but there will still be questions like this where we want to know, are two groups of people doing something differently? All right, has something changed over time? All right, in order to answer these questions, we need inferential tests. All right, so the first big thing that we need to keep in mind here, in terms of terminology that we need to use when we talk about statistical testing, is this idea of statistical significance. All right, and so this phrase that you've probably heard before, that something is statistically significantly different, or there is a statistically significant relationship between these two things. Importantly, a statistical difference is not the same as an algebraic difference. All right, algebraic, just another word for math. Excuse me, I'm going to sneeze. Okay, sorry about that. I can't pause the video. An algebraic difference means that the two numbers are just not the same. All right, so if we look back at these two examples, customer satisfaction last year was 92%. This year it's 93.5%. There is an algebraic difference there. 92 is not the same number as 93.5. Women had a mean of 6.4, men had a mean of 7.0. There is an algebraic difference here, all right? 6.4 is not the same number as 7.0. In statistics, though, in these inferential statistics, we're looking at something a little bit different, all right? A mathematic or algebraic difference exists if numbers are not exactly the same. But when it comes to statistical difference, there's an additional burden of proof that needs to be met. All right, so the first thing that we need to think about is why two numbers might be mathematically different, but not statistically different. All right, and so let's turn to our imaginary chalkboard here. If I can get this bigger. You guys, please excuse my horrible manicure that is all chipped right now, but all of the nail places are closed and I can't do it at home because I never learned how to do girl things. So anyway, so just don't judge me for it. Okay, let's say that the women's mean was 6.2, the men's mean was 7.0, all right? This was data that we got from a sample of 1,000 potential customers, all right? Lowercase n is telling us that this data is coming from a sample, all right? So we have some population. Our population would be denoted with a capital N, and I don't know exactly what our population is, but it's some number greater than 1,000, all right? So we have a sample drawn that is some subset of our population. And that subset of our population, the women on average are reporting a purchase intention of 6.2, and the men on average are reporting a purchase intention of 7.0. All right, now there are at least two reasons why we could find this result in our data set. First possible reason is error. All right, remember we talked about sampling error, that we have a population of people. Let me adjust this camera. We have a population of people. We draw some subset of that sample and we get their answers. But let me change colors a little bit here. If we had talked to these other people, all right, so if we talked to the people who were not sampled, we would have found a different mean for the men and the women. All right, so we get this result that's our sample, but we know that what we get in our sample is not equal to the population mean. Sorry, this should be women. Is not equal to the population mean for the men and the women. All right, mu is the mean in the population. X bar is the mean in the sample. We know that what we draw in our sample is not exactly equal to the true population mean, because if we had talked to a different people in our population, we would have gotten slightly different answers from them, right? And so as a result, because we're missing these people's answers, the sample mean that we calculate is not exactly equal to the population mean. All right, so one reason why we're seeing a difference between men and women in this sample could just be error. It is possible that if we had conducted a census, that we would have found that the population for the men equals the population mean for the women. So men and women really are no different in terms of their purchase intentions, and we're only seeing this result in our sample because we only talked to a subset of the population. And if we had talked to everyone in the population, we would have seen a different result. All right, so that's one possibility. Another way, or another possible explanation for this result that we're seeing, sorry, let me learn how to adjust this camera, is that we are seeing this difference in the population, or in the sample, because there really is a difference in the population. All right, so it's possible that we are seeing this result in our sample because at the population level, the mean of men is different than the mean of women. And because that's true at the population level, we are seeing that result in our sample. All right, so our sample is just accurately reflecting something that really does exist at the population level. All right, so we have these two possibilities. All right, and because these two possibilities exist, we can't just look at information from our sample and say, well, if there's a mathematical difference, that necessarily means that there's a difference between men and women, because it's possible that that difference that we're observing is due just to error, all right? Or it's possible that that difference that we're seeing is reflecting some real population level difference. Let's pull these slides back up. All right, so two numbers that we observe in our sample could be mathematically different, but not statistically different because of chance and sampling error. All right, so because of this fact that we talked to a subset of the population, as a result, we know that the answers that we see in our sample are not exactly equal to the population values, and it's possible that those differences that we're seeing exist only because of chance and sampling error. All right, so in order for us to conclude that there is a statistically significant difference, that means that the difference between the numbers that we observe has to be large enough that it's unlikely to be due to chance or sampling error. All right, let's see this visually, and then I'm going to write it visually on our document camera here in just a second. Let's imagine that you do a taste test with 1,000 customers to see which of two product formulations consumers prefer. All right, and so you give everyone these two formulas in unmarked cups, you ask them to consume the products, and then they have to indicate which cup they preferred, the cup containing Formula 1 or the cup containing Formula 2. And your results are that 49% of customers prefer Formula 1 in the sample, and 51% of your sample prefers Formula 2. All right, and so now you have this question, is Formula 2 preferred? All right, do I think that this evidence in my sample is indicative of a real population level preference, right, for Formula 2 over Formula 1, right? That's the inferential part. We are using information from our sample to make an inference about the population. So do I think that this evidence from my sample is strong enough to suggest that at the population level, people really do prefer Formula 2? Or do I think that I'm seeing these differences in preference for Formula 1 and Formula 2 in my sample just because of chance and error? All right, it's just a fluke of my specific sample. If I had talked to a different sample of people, maybe I would have gotten a different result. So first question, is there a mathematical difference? Yes, there is. All right, 49 is not the same number as 51. So there is some evidence of a difference between these numbers. The second question is there a statistical difference? Are these statistically significantly different, meaning the difference in preference for these two formulas is so large that it is unlikely to be due just to chance and sampling error? All right, so we have preference for Formula 1 and preference for Formula 2. We can construct confidence intervals, right, around these preferences. I don't know if you recall from the lecture about sampling, but when you have a sample size of 1,000 and you're asking people to choose between two binary nominal options, so Formula 1 and Formula 2, they have two options, two nominal options, that gives us a 3% margin of error. All right, so if we look at this number line down here representing the possible answers that we could have gotten, then this, I don't know, it's supposed to be like a purpley kind of color. I'm not sure what color it comes up on your screen. This line, this curving line here represents the confidence interval that we can construct to estimate the population preference for Formula 1. All right, so 49% plus or minus a 3% margin of error. All right, this is our estimation of how much sampling error exists in our sample. This means that we are 95% confident that the true preference for Formula 1, the true population level preference for Formula 1, falls between 46 and 52%. All right, so this is our best estimate, given our sample size and the results that we found. We can do a similar thing for Formula 2. All All right, we're 95% confident that the true population preference for Formula 2 falls between 48% and 54%. All right, some of you may be looking at this and thinking, I see a problem. All right, so I see the issue here. If we're trying to ask, do people really prefer Formula 2 to Formula 1? The issue here is that there is a lot of potential. Now the slides don't want to work. There you go. There's a lot of potential overlap in preference for Formula 2 and Formula 1. All right, so what this means is, given the data we have at our sample, it is possible that the true population level preference is actually 50-50. All right, because both the red line and the purple line exist at this 50 mark, and so the population preference could be 50-50. It could also be 51 for purple and 49 for red. All right, so 59 preference for Formula 1 and 49% preference for Formula 2. So the result could actually be the opposite of what we found here, or it could be an even more extreme sort of case where 52% of people prefer Formula 1 and only 48% of people prefer Formula 2. The point here is that in this entire range, it is possible that the true preferences are either equal or the opposite of what we actually found in our sample, given the ranges of our confidence interval. So once we account for how much error is playing a role in these specific answers that we found in our sample, it's possible that at the population level, there really is no difference between these groups. All right, so if we were going to conclude statistically that there was a difference between these groups, we would, this is not exactly true, but it's true enough for us, we would need to see curves here that do not overlap. All right, because what would be happening here, let me actually draw this on. Let me see what I have to do here to get this screen off. All right, back to the document camera. Let's say that we asked about preference for these two things. All right, what's happening here, let's go back to let's get rid of this 45, and let's say that we have the men or the women have a mean of 6.2, and the men have a difference or a mean of 7.0. So what's happening here when we think about this difference from a statistical perspective, there is all of this difference between men and women that has to be explained. All right, something has to explain this difference that we're seeing between the men and the women. We do not expect that the men and women at home just close their eyes and randomly selected a number on that scale on the survey. So something has to explain why in our sample we see women with a mean of 6.2 and men with a mean of 7.0. As we have mentioned over and over again, some error is always present, right? And so the question that we're asking when we do these inferential tests is, can this entire difference be explained entirely by error? All right, and so what we'll see is that sometimes, if you calculate the margin of error, sometimes this would be, perhaps our confidence interval for this number. In this case, this much of the difference can be explained by error. All right, so this is reflecting the confidence interval that accounts for the margin of error in our measurement. And so once we account for the margin of error, we have now explained this much of the difference between the men and the women's answers, but there is still this amount that needs to be explained. All right, let me bring in another color here. We still have this much difference between men and women. It cannot be explained just by error. All right, so once we account for error, if there is still a difference left over here, then our only explanation for this is that there must be a population level difference. All right, because the difference that we observed in our sample is so large that it cannot be explained just by error. And so what's left over is to say, well, men must really like this thing more than the women, and that's why we're seeing this in our sample. All right, over here, once we accounted for error, there was no more difference between the preference for these two formulas. There was no additional difference that needed to be explained. And so as a result, in this specific case, if we were to do the appropriate test, which would be a chi-square test, we would see that there was no difference in preference for these two formulas, because the entire difference that was observed in the sample can be explained by the margin of error. All right, so when we talk about something being statistically significantly different, the question is, we found a difference in our sample. There is some evidence to suggest that maybe there's a difference at the population level, but can what we observed, that difference that we observed in our sample, be explained entirely by error? If yes, then we conclude it might just be error, right? There might not really be a population level difference. It might just be sampling error explaining this. But if it can't all be explained by error, and there's some more difference left over that hasn't been accounted for, then we say this must be reflecting a population level difference. These are statistically significantly different. All right, when we do these tests, it's called hypothesis testing. All right, so we write out our hypotheses and then we test to see which hypothesis is more supported. All right, so a hypothesis is an assumption or theory that a researcher makes about some characteristics of the population being studied. All right, so for example, I think women spend more money than men on clothing. I think men spend more money on dining out than women. I think older students spend more money than younger students on groceries. I think students in the Greek system dine out more for meals than other students, etc. All right, you have some belief about a pattern that you think might exist in your data, and then you want to look to see, is that pattern really there? And is the pattern strong enough that I think it's reflecting a real population level pattern? That if I had conducted a census, I would expect to see that same pattern in the population, that it's not just a fluke of my sample, it really is there at the population level. When we state the hypothesis, it has to be stated in two forms. All right, let's pause for just a second. Can you guys remember the two forms that the hypothesis takes from your statistics class? The null hypothesis and the alternative hypothesis. All right, the null hypothesis is often referred to as the status quo hypothesis. And in terms of trying to remember the difference between these, I would recommend thinking about the null hypothesis. Null means nothing, all right, or zero. That's why the null hypothesis is denoted H0. All right, the null hypothesis is the hypothesis that nothing happened. There was no difference between groups. The intervention had no effect on the outcome you were interested in. There was no relationship, there was no difference, etc. So once we get to learning about the specific tests and setting up the null and alternative hypothesis for each of those tests, you'll see that the null hypothesis always takes the form, there was no difference between what I observed and what I expected. There was no difference between men and women. There was no relationship between these two variables. All right, so it's always no difference, no relationship, etc. The alternative is the alternative that's based on your theory, which is generally that there is some difference. All right, there is a difference between some groups. The advertisement increased purchase intentions, the sale increased money spent in the store, etc. The alternative hypothesis is just the hypothesis that something happened, that there is a difference or a relationship at the population level. All right, so the classic question, the one that's hard to wrap your head around, the one that makes statistics seem confusing and we have no idea why we have to do all of this. Why do we need two types of hypotheses to test the significance of a single result? All right, if I find in my data set that the women have a mean purchase intention of 6.2 and the men have a mean purchase intention of 7, I have this one question. Do men have higher purchase intentions than women? Why do I need two hypotheses to test that single question? The reason is because of that word. It's always the answer. If you're ever struggling with what's the answer is always error. It's because of error, right? Because we drew a sample, we have sampling error, okay? Remember, sampling error is referring to the fact that because we are talking to only a subset of the population, we know that the answer that we get from our sample is not exactly equal to what the entire population would have told us, because the answers of the people we did not speak to would have changed the response. All right, so we know there's sampling error anytime we talk to a sample. And because that error exists, we can never know 100% that something is true. Right? The only way to know 100% that something is true is to conduct a census. All right, and even then, you would have to conduct a census where nobody lied or unintentionally, falsified their answers, et cetera. All right, so if you think back to that example that we did on the board about trying to calculate the true height of men at Ole Miss, we said that in order to learn that true value at the population level, we would have to conduct a census, and we would need to get measurement that was error-free. So we could have no bias in our measurement of heights. All right, and because that never happens, all right, we never conduct a census, we never have perfectly bias-free measurement, we can never know that the result that we find in our sample is exactly true, but the statistics can tell us the odds that something is false. All right, so it can't tell us the likelihood that something's true, but it can tell us the likelihood that something is false. All right, and so because of this, we reword our hypothesis to create a hypothesis we hope is false. All right, so if our alternative, or if the thing that we're interested in is, are men different than women? All right, then we reword this into something we hope is false. All right, so then our null hypothesis becomes men are equal to women. All right, and so then we look to see, is that null hypothesis false? All right, what are the odds that that null hypothesis is false? Because if the odds are good that that null hypothesis, that men and women are equal, is false, then that suggests that the alternative is true, with true in air quotes, because it can't actually be true, but it does imply that the alternative is more supported. All right, so we basically set up this straw man, and then we look to see what are the odds that that straw man is false. And if the odds of the straw man being false are really high, then we're going to reject that null hypothesis, and we're going to say we side with the alternative. All right, we conclude that there is a difference between the men and the women. All right, and so here's this. Why can't we ever say something is true? It's because of chance and sampling error. All right, before we get into this, I want to go back to this whiteboard for just a second so we can see some more about the null hypothesis. Sometimes when you get a sheet of paper that doesn't have dots all over it, let's say we find, let me switch to a regular pen because this Sharpie's dying on me. Let's say that we find in our sample this result, that the mean for women is 6.2 and the mean for the men is 7.0. And we want to know, remember our goal always is there is some population, and we have this question about the population. Is the mean for the women equal to the mean for the men at the population level? Right, this is our population over here with all the people in it. We, in order to learn that, right, with perfect accuracy, we would have to conduct a census, and we would have to have bias-free measurement, right? But those things aren't going to happen, so we settle for the next best option, which is that we draw a sample, and that sample gives us this information over here, right? The subset of the population has told us that the women's purchase intentions average 6.2 and the men's purchase intentions average 7.0. But remember, our goal is still to know what's true at the population level, right? And because we couldn't conduct that census, our next best option was to calculate some findings from the sample. And then we're going to use this information from the sample to draw an inference about the population, all right? Based on what I learned from the sample, what do I think is true for the population? All right, because our goal is always to know about the population. If you think about our ADHD survey, our goal is to learn about Ole Miss students' behaviors, all right, regarding these ADHD medications. Our goal is not just to know how your friends use them, right? We want to know about all the students on campus, and we're going to use the information from your friends to make an inference about the entire student population. All right, so we get this data from our sample, and we see this pattern in the sample that suggests that men are more likely to buy this product, or they have higher purchase intentions than the women. But as we mentioned before, there are two possible reasons why this could happen. All right, the first possible reason is error. The second possible explanation for this difference is that there really is a population level difference. These two possibilities are expressed in our null and alternative hypothesis. All right, so our null hypothesis would say that the mean at the population level, the mean for the women is equal to the mean for the men. Sometimes I think that students get frustrated by this because they say, how can we set up a null hypothesis? And especially if we fail to reject that null, how can we look at these numbers and conclude the population mean for the women is equal to the population for the mean for the men when we see this difference in our sample? The null hypothesis is not blind to that difference that you're seeing in the sample. What the population, or what the null hypothesis is saying is, I see the difference you observed. Sorry, my hand's running into the end of the table, so it's going to get weird. I see the difference you observed in your sample, but that difference can be explained entirely by error. At the population level, I don't think there is a difference. All right, so the null hypothesis recognizes and accepts, right, that you see a difference in your sample. And when the null hypothesis says, I think the population mean for men is equal to the population mean for women, it's not ignoring that difference, right? It's just saying, yes, you saw a difference in your sample, but the analysis tells us that that difference can be explained entirely by error. And as a result, because we're trying to make an inference about what's true at the population level, if this result from your sample can be explained entirely by error, then it doesn't provide good evidence that there really is a difference at the population level. This result could just be a fluke of the specific sample that you drew from the population. And if you had gotten a different sample, right, for example, if we had sampled these people in the red circle, maybe we would have gotten an answer where the sample mean for the men and the women was equal. Right? And so maybe it's just a fluke of the specific people who ended up in this sample that we're seeing a difference in the sample, right? It's just chance and sampling error. And at the population level, I don't think there really is a difference. All right, so the null hypothesis is paired up with this explanation of the data that it's just error driving any effects that you see in your sample. The alternative hypothesis takes the side of this explanation, right? The alternative hypothesis says that there is a difference between the men and the women at the population level, right? And specifically, it is saying that the difference in your sample is so large that it is unlikely to be due just to chance or error, right? It must be reflecting a real population level difference. All right, so the alternative hypothesis sees the same pattern, and if the result comes back and says this difference is so large that it's unlikely to be due just to chance and error, then we conclude that we're seeing this difference in the sample because there really is a difference in the population. And if we had drawn a different sample of people, or if we had conducted a census, we would expect to see a difference between the men and the women. All right, so the population mean for the men would not be equal to the population mean for the women. And so when we do these inferential tests, what the inferential test is doing is it's saying, okay, you have gotten some evidence in your sample. The question now is, how strong is that evidence? If the evidence is pretty weak, then we say it's probably just error. All right, and so there's probably not a population difference. If you're seeing this in your sample, this weak difference that you're seeing in your sample can be explained just by error. But if the difference that you're seeing in your sample is very large, then the result will say it's unlikely that you would find a difference this large, right, just due to chance and sampling error. It's a very improbable event that that would happen. And so this must be reflecting some real population level difference. You must have found that difference in your sample because the difference really exists in the population. And so your sample is just doing a good job of reflecting what's true at the population level. This, of course, raises the question of how large does that difference need to be for us to consider it so large that it's unlikely due to just chance and sampling error. right? We're getting here in the slides. All right, so the previous slide said we have to set up this null hypothesis because we have to look to see which one of these hypotheses is more likely to be false, and that's how we make a decision about which hypothesis we're going to go with. All right, but when we do this, we can't be 100% confident. All right, we can't ever know with 100% confidence that something is true. So the level of confident that we typically are, I'm sure some of you are whispering to yourselves, 95%. We always have this 95% confidence number, and that 95% is coming from our willingness to accept false positives and false negatives. All right, so let's get into some technicalities here for just a second. When we make a decision at the result of our test, all right, that we're going to reject the null or we're going to fail to reject the null, meaning that we either side with the null hypothesis or we side with the alternative hypothesis, because we can't be 100% sure about our answer, there's a chance that we're wrong, all right? Because error is at play here. Due to that error, we could make a wrong choice. A type 1 error occurs when you reject the null hypothesis when it is in fact true, all right? So in reality, at the population level, there is no difference between men and women, but your test tells you there is a difference. So you reject the null, you conclude that there is a difference between men and women, but you're wrong when you do that. If you could conduct a census and reveal the truth about the population, you would have learned that there really was no difference, so you were wrong when you rejected the null hypothesis. This is called a type 1 error. All right, it's a false positive. All right, it's saying there's a difference when in fact there is no difference. All right, and the probability of committing a type 1 error is denoted alpha. We're going to get to that in just a second. The other kind of error is a false negative. All right, this is failing to reject the null, all right, siding in favor of the null, saying that nothing is happening when in fact something is happening, all right, when in fact there is a difference. All right, it's failing to recognize a difference in the population when one really does exist. And the probability of committing a type 2 error is denoted beta. So most people, when they first start learning about this, they say, well, why don't we just try to minimize our chance of committing both types of errors, all right? Why don't we just set up the test in a way that we're unlikely to commit either one of these types of errors so we can get the most accurate result possible? The problem is that alpha and beta are inversely related to each other, all right? So if I can get the pen here, everyone's favorite pen. When alpha increases, beta decreases, all right? So minimizing your chance of committing one increases your chance of committing the other. Right? And so you have to basically decide which one of these is more important to you. And luckily, we don't have to decide because someone decided a long time ago. I don't know the name of the person who decided this a long time ago. I'm guessing that it stemmed from medical research. But a long time ago, people decided that type 1 errors were worse. All right. So if we think about this in the context of medical research, let's say that you are testing a new pharmaceutical drug and you're testing to see, does it really result in lessen symptoms or eradicating the disease that it's supposed to be treating? Committing a type 1 error would mean that you said the drug works when it doesn't really work. Right? And so a long time ago, people decided that that was the worst thing that you could do. Right? Say that a drug was working when in fact it was not working, that it was worse than the alternative of failing to recognize a good drug that actually existed. All right, so we're going to talk more about these on the next screen, but to try to keep this in your head, type 1 error, false positive, telling someone who is not pregnant that they are pregnant. A type 2 error is a false negative, all right, telling an obviously pregnant woman that she is not pregnant. Or if you can't keep that example, I like this one. Just remember the story, The Boy Who Cried Wolf. All right, so I think we all know the story about the boy who cried wolf. The boy was bored, so he yelled to people that there was a wolf when in fact there was not one. And he did that over and over again until the townspeople started ignoring him. And at that point, a wolf did come along and no one came to save the boy because they assumed he was lying. All right, so in The Boy Who Cried Wolf, the boy causes type 1 and type 2 errors in that order. All right, so first, he leads everyone to believe there's a wolf when there is none. That's a type 1 error, saying that something exists when it does not. And next, they believe there was no wolf when in fact there was one. All right, and that's a type 2 error, concluding that nothing is happening when something really is happening. All right, so if you substitute the word effect for wolf, you're done. All right, you can figure out what kind of error you have here. All right, when we do this hypothesis testing, we have two possible outcomes. All right, we're going to reject the null hypothesis, which means we conclude there's sufficient evidence to support the alternative. All right, or we're going to fail to reject the null hypothesis, meaning there is insufficient evidence to support the alternative. All right, and so as a result, we're going to side with the null hypothesis and conclude that there's no difference here or no relationship. This does not mean the null hypothesis is true. It simply means we failed to provide sufficient evidence that it's false, right? And that is a lot of doublespeak happening in there. So I want to go back to our whiteboard again to talk about an example of this, and we can see the errors happening in here as well. All right, let's think about a show. If you need a show to binge watch, if you have, I don't remember where you can binge watch it, maybe on Hulu, maybe on Netflix. Every woman's favorite TV show, Law and Order SVU. Whenever we're in class, I always ask, how many of you guys watch Law and Order SVU? Like one guy raises his hand, but all the women raise their hand. And I really don't understand this because Law and Order SVU is just a show about women being raped and murdered, and yet women love watching it, right? Maybe it's because Elliot Stabler is so cute, but regardless, we all have a legal education stemming from watching Law and Order and shows like it, all right? And so we can answer some questions about the law, about hypothesis testing by thinking about our legal educations. All right, let's imagine that there is some person who's being investigated for a crime. All right, so there has to be some evidence that this person committed the crime, all right? Otherwise, they wouldn't be being investigated, all right? The evidence might not be very good, but there's some evidence. All right, we can think of this as evidence from our sample. All right, so there's some evidence to suggest that someone did something, all right? And so this person is going to a legal trial to make a determination about whether they are guilty or not guilty. And in this, we have two players. We have the prosecutor, whose job it is to provide evidence that the defendant is guilty. And we have the defendant who, despite what always seems to happen on TV shows, I'm sorry, not the defendant, the defense attorney. The defense attorney's job is not to prove the innocence of his client. The defense attorney's job is to negate the prosecutor's evidence. All right, so the defense attorney's job is just to poke holes in the prosecutor's story. All right, in TV shows, they always, come up with some smoking gun that proves the person wasn't there, but that's not how it works. In the real world, the defense attorney just negates the prosecutor's story. All right, so when you come into, if you are the defendant coming into the courtroom, there are two possibilities set up. All right, the default in the US is supposed to be that you are not guilty, all right, until proven guilty. All right, you're innocent until proven guilty. So the null hypothesis is that you are not guilty. The alternative is that you are guilty, all right? And it's the prosecutor's job to provide strong enough evidence to secure a guilty verdict from the jury, all right? And it's the defense attorney's job not to prove innocence, but to just say, this is bad evidence, all right? This is not strong evidence, and as a result, you should come back with a not guilty verdict. All right, so the prosecutor provides all their evidence, the defense attorney tries to poke holes in it. At the end of the day, there is some evidence. The jury goes out and they come back with two verdicts, right? And so the two verdicts are either going to be not guilty or guilty. Importantly, the jury never comes back and says innocent. That's not a possibility, all right, when you are in the courthouse. The possibilities are that you are guilty or you are not guilty. Now, how does this relate back to these type 1 and type 2 errors? If the jury says not guilty, does that mean with 100% confidence that the defendant is innocent? No, it does not. All right, if a verdict comes back of not guilty, that does not mean that the defendant is innocent. It means the evidence was not strong enough, all right, to support a guilty verdict. It's possible that the jury says not guilty and the defendant really was guilty. They really did do it. And if the defendant really was guilty, jury has committed a type 2 error, right? They have sided in favor of the null hypothesis when the alternative hypothesis was true, right? Of course, they can't know that. They don't know they're committing an error when they do that. It's just a question of how strong was the evidence. And if the jury decides that the evidence was not strong enough, right, having some evidence does not mean that the defendant is guilty. The question is, how strong is the evidence? If the jury comes back guilty, does that mean 100% that the defendant actually did it? Again, no. All right. If defendant really was innocent, jury has committed a type 1 error. All right, so they have rejected the null when they should not have. All right, they've rejected the null when in fact the null hypothesis was true, and that's a type 1 error. All right, and so now we can see where we have to make a decision about which one of these we want to be more focused on. Do we want to focus on maximizing the likelihood that we penalize people who really are guilty? All right, so we don't ever want to say not guilty. We don't ever want to let a criminal go. Then we would focus on type 2 error. If, however, we want to focus on minimizing the odds that we put someone in jail who actually was innocent, then we focus on type 1 errors. All right, we say that the burden, and this is how our legal system is supposed to work, that the burden is on the prosecutor to provide a strong enough case to support that this person should be jailed. All right, so you can't just come in with a little bit of evidence. You need to have a lot of evidence to convince the jury that this person really did commit the crime, because we want to minimize the number of people who are serving jail sentences for crimes they did not actually commit. All right, and so because of this, we focus on type 1 error, hypothetically, in our legal system, and we also focus on it when we do hypothesis testing in statistics. All right, and so the next question is, if we're trying to minimize type 1 errors, meaning that we need strong evidence before we decide to reject the null and conclude that there really is a population level difference or there really is a population level relationship, how strong does the evidence need to be? Right, and in statistics, how this gets handled is that we set alpha. Remember, alpha is our type 1 error rate at 0.05, meaning that we are only willing to reject the null hypothesis when there is a 5% chance or less that we are wrong to do so. All right, so the evidence has to be strong enough that there is only a 5% chance of being wrong when we reject the null hypothesis. This is in the slides, but I'm just going to stick to the paper for a minute. When we make a decision about rejecting or fail to reject the null hypothesis, let's go back to our example about the men and the women and their purchase intentions in the sample. If the women's purchase intention was 6.2 and the men's was 7.0, we want to know, based on this sample, is there a real population level difference between the men and the women? We would need to do what's called an independent samples t-test, which you'll learn about in 2 or 3 videos. This t-test would come back and, with a t-statistic. The t-statistic would summarize the magnitude of the difference between these 2 numbers. And along with that t-statistic, you would get a p-value. All right, now, I minored in statistics when I was undergrad, which is relevant only to say that I took a bunch of statistics courses when I was undergrad. And despite the fact that I took so many statistics courses, it took I think 3 or 4 classes into my statistics minor before a professor actually stood up in front of the class and explained to us what the p-value meant. Right? I guess the others assumed we were reading it in the textbook. I was undergrad too. I didn't do a great job of reading the textbook. Right? So I was always a little, like I knew this rote memorization, how do we deal with the p-value, but I never really knew what the p-value meant. Right? And so for those of you guys who need to understand what things mean, right, to understand the logic of what's going on here, I'm going to let you in on the mystery, all right, of what the p-value means. You're going to get a test statistic. It doesn't matter if it's t or chi-square or a correlation coefficient. you're going to get a p-value that goes along with it. And what the p-value is telling you, p is equal to the probability, all right? It's called p because it is a probability. P is the probability that you would find the difference you found in your sample or greater. All right, I say difference here because we're looking at this t-test. This could be a relationship. A broader term would just to say effect or pattern, right? The probability you would find the pattern that you found in your sample due only to chance or sampling error. All right, so P is the probability that you found this difference in your sample just because of chance and error. All right, and so when you have, if you find in your sample the mean for the men and the mean for the women are very close together, then you're going to get a large p-value. All right, because if these means are very close to each other, remember we have these two possibilities. I'm finding this difference in my sample either because there really is a population level difference between men and women, or it's just a fluke of chance and error. This specific difference right here is not very strong evidence of a population level difference at the, in the full population. So there's very good chance that we're finding this just because of chance and error. But as those means get further and further apart, the odds that you would find this large of a difference due just to chance and sampling error gets much smaller. All right, so the odds of finding a difference this big, if in fact there were no difference at the population level, means that we have a very small p-value. All right, just like in the court case, when we do these hypothesis tests, there is a default assumption that the null hypothesis is true, all right, that there's no difference. All right, and so we start off with this assumption that there's no difference, and we have to provide strong enough evidence to convince us otherwise, all right, to reject this null hypothesis. And so the question is, if we assume that at the population level, men and women are the same, if we make this assumption that this is true, that if we conducted a census, we really would see at the population level that men and women are exactly the same in terms of their purchase intentions way up here, then it would be very unlikely, if men and women in the population were true, it would be very unlikely that we would manage to draw a sample that found this big of a difference. And that's why we would get a very small p-value, because it would be very improbable. The odds of happening to draw names from an equal population such that the women in our sample all tended to hate the product and the women or the men in our sample all tended to love it, the odds of that happening are very low. However, if the null hypothesis is true and at the population level, men and women like this product equally, it would be very possible to find a sample of people where the means were almost the same, just a little bit different. It would be very easy to find this kind of sample from a population where the null is true. And so here we have a high p-value. All right, so if the odds of finding this in a population where this is true, if the data that you find from your sample is incredibly unlikely to exist in this population, then we say this must not be true. So we reject the null. All right, we start with this assumption that this is true, but if our data suggests that we've drawn a sample and the odds of getting this kind of a sample, if this were true, are incredibly low, then we're going to say this must not be true. That assumption that we started with must be a bad assumption. So we're going to assume that that's not true, and we're going to reject the null. Thinking about this in the legal terms, sorry, let's get our SVU statistics happening here. We start with the assumption that a defendant is not guilty. Okay, so if the prosecutor comes back and says that the defendant had the weapon, was covered in blood, dating victim, there was a life insurance policy, all right? So if all of these things exist, There's all this evidence to suggest that the defendant did it. What are the odds that you would find a person where all of these things are true and that person was not guilty? The odds would be very low. And as a result, we would say this must not be true, and so we're going to come back with a guilty verdict. However, if the prosecutor, the defendant starts out with a not guilty assumption, if the prosecutor comes in and says the defendant knew the victim, that's it. They just knew the victim. You could find all kinds of people who knew the victim and were not guilty. So the odds of these two things existing simultaneously are quite high. Right? There are going to be lots of people who knew a victim but did not kill that victim. And so here, the odds of finding that result, if this were true, is going to be pretty high. And so we are going to fail to reject the null, all right, and keep this assumption of not guilty. All right, so we always start with this assumption that the null is true, all right, in this specific case, that there is no difference between men and women in the population. And the question is the evidence strong enough for us to throw out this assumption? All right, for us to say the men and women must not be the same, because it's incredibly unlikely that I could find this difference in my population if the men and women were actually the same at the population level. So the men and women must not be the same, and I'm going to reject the null. The point, all right, at which we decide that the evidence is strong enough is at 0.05. This is because we set alpha, our type 1 error rate, to 0.05. All right, so the way that we can interpret this is if your test result comes back with p equals 0.05, that means there is a 5% chance that you could find a sample this different in a population where there really was no difference. All right, so there is a 5% chance that this result is due just to chance and sampling error. And that means that if you reject the null and you conclude that there is a population level difference, there is a 5% chance that you're wrong. We are only willing to tolerate a 5% chance of being wrong. We're only willing to have a 5% type 1 error rate. So if p is less than 0.05, we are going to reject the null, because that means there is less than a 5% chance that we are wrong when we reject the null. And if p is greater than 0.05, we are going to fail to reject the null. All right, and these are our decision rules. We will talk about them over and over again when we talk about the statistics that need to be done, you know, how we do chi-square tests and t-tests and correlation and everything like that. But the key thing here is remember, the p-value is telling us the probability that you would find the pattern you found in your sample due only to chance or sampling error. Remember, we have the null and alternative hypothesis. The null hypothesis is saying difference in sample due to error. The alternative is saying you saw that difference in your sample due to population level difference. All right, so if the probability that your result is due only to chance or sampling error is only 5%, that means basically there's only a 5% chance that this is right. That's a very small chance that the null is right, so we're going to reject the null and side in favor of the alternative hypothesis. But if the p-value is even just 0.06, that means there is a 6% chance that we're wrong when we reject the null hypothesis. That is greater than the 5% chance of being wrong that we're willing to accept. And so if your p-value is 0.06, we're going to fail to reject the null at that point. We're going to say there's evidence, but the evidence is not strong enough for me to reject the null. Right? I have to be conservative and say, while there is evidence, the evidence is not strong enough to reject that null hypothesis. Right? And so that's what's down here. When we have these possible outcomes of rejecting and failing to reject the null hypothesis, we have to use our p-value and compare it to alpha to decide if we're going to reject or fail to reject. Importantly, as I was mentioning with the legal sort of metaphor, if we fail to reject the null hypothesis, this does not mean the null is true. It simply means we didn't have enough evidence to suggest that it was false. All right, same with rejecting the null. There is a chance although it's a small chance, all right? If we get P equals 0.02 and we reject the null, there is still a 2% chance that we were wrong when we did that, all right? But we're minimizing our odds of being wrong here. And so sometimes our sample will provide what looks like strong evidence, but because we are conservative when we do these tests, the evidence has to exceed a threshold, a fairly high threshold. And if it doesn't exceed that threshold, then we fail to reject the null, and we conclude that our data does not provide sufficient evidence to suggest that there's a population level difference or relationship. All right, so normally in class at this point, there would be, you know, some question and answers. People always have questions on this day. People are a little chattier on this day. I'm really sad that we have to do this virtually instead of being in the classroom. If you are watching this, hopefully you're watching this. As you're watching this, please write down questions as you have them. I know it's too late. I should have said this at the beginning. I'll label the YouTube video. Write down your questions as you have them. As long as I have access to Connor 111, I will come in here and answer your questions, using the document camera, as though we were writing on the board, to try to make sense of the null and alternative hypothesis and when do we reject the null and stuff like that. So if you have questions, please comment under the YouTube video with your questions. Please email them to me and I can try to come in and make a video answering some of those questions. Okay, otherwise, wash your hands. All right, stay inside. I'd like to say see you soon. That's probably not going to happen, but have a good day and I'll see you for the next video.